configuring Smaart. Now, I've already got mine configured, so I'm going to start a new tab in here. So just ignore all these things that I have listed over here. When you guys open it, it's going to be a totally blank slate. So right here, you're going to click on this little hammer and wrench icon. And none of these things will be over here. And you want to click on New Tab. And we're just going to call this Demo. Now you will come over here in the bottom corner and select New Spectrum Measurement. We're going to call this Microphone. And then you want to make sure that you select the interface that you're actually going to be using. In my case, this is the UM404 HD. Great interface for inputs, 4 channels of preamps for $100. Totally unusable outputs. So if you ever decide to buy this item, you will not be able to use the outputs on it for measurement purposes. But it's a really great thing to take with you when you're on the road. If a stagehand knocks it off a loading dock and shatters it, you're out $100. Not that big of a deal, as opposed to spending $500 or $600 for a 4-channel Focusrite interface. But anyways, so we're going to make our first new spectrum measurement device, calling it Microphone, and we're going to make a second one. And we're going to choose the channel of which we are going to be putting our reference signal through. Now that we've done that, we want to do new TF measurement for our transfer function. Again, select the interface which you are using, and then you want your first channel to be set up as your microphone or your measurement channel. The second channel here, your reference signal, is going to be whatever channel your reference signal is coming down from your spectrum measurement. Does that all seem clear? Mm-hmm. Cool. And we'll just call this FFT1. Cool, so that's all created now, and then I'm going to click on my demo tab here, and we can see that we've got our 2 channels showing up. And there's our mic channel, and I'll turn the reference channel on here, and as I send pink noise down that, we should be able to see that come up. Now, something to double check, it should do this automatically, but still a good idea to take a look here. You want to open up the signal generator window and make sure that you've got the appropriate device selected here. As I mentioned, the outputs on this UMC 404 are not usable for measurement purposes, so I'm just coming out of the built-in output on my computer. And here you have the option of choosing pink noise, sweeps, sine waves, all that kind of stuff. For this, we're going to go with pink noise. So then you can come down here, turn pink noise on. And now what I just did there was to store snapshots of each one of those. And you do that by hitting spacebar in the software. So in pink here, we have a snapshot stored of the reference material coming out of the computer directly into the console and then back into the computer. And then in green, we have the reference mic. Now it's important when you're operating within the single channel window, the main purpose of this is that you want to make sure that you're operating at equal amplitude between your reference signal and your microphone signal. So you see how, for the most part, these 2 traces are overlapping seamlessly with each other. That's what we want to see here. So now that we're, and let me mention this, just some of you might have noticed this already. On my reference signal, you see this bump that I have here around 13K. So this particular microphone has just indicative of that capsule design, is a bump around 13K in the microphone itself. So by me adding that into the reference signal, then I don't have to look at this spike showing up in the FFT. It'll look more even. So nothing crazy, that's in there intentionally. And we're going to go to the transfer function window. You can go there by toggling between these three different buttons, or you can just hit the number 6 on your keyboard. And when you first open it, you may see this window up in the top. This is the live impulse response. You're not going to need to worry about that for anything you're going to be doing. So you want to make sure that that's closed out. Now that we've verified that everything is working within the software, we want to go up here to our options menu, select general, and so I don't have to hear that beeping. You want to make sure that your cursor frequency readout is set to frequency and wavelength, so that way you can see if you're measuring 1K, 2K, whatever it is, you're able to see the actual size that wavelength is. That's a pretty important feature for when it comes to actually spacing speakers out in a system design application. You want to make sure that your cursor time readout is set to milliseconds. If you want to use distance, totally fine. It ends up being too much information on the screen for me to read, so I choose not to do that. And then I believe out of default, Smaart is going to be set to speed of sound in meters and temperature in Celsius. You want to change that to imperial. Moving into the spectrum tab, this is what I mentioned earlier about the data windowing. You want to set this to Blackman-Harris. If you were going to do a single channel measurement of how much harmonic distortion a speaker had, you could use flat top. You could also use Hahn for any system measurements, but just so everybody's looks the same, we should stick to Blackman-Harris. You want to make sure your FFT size is set to 32K. Your frequency scale is set to 1/3 of an octave. And a little bit of personal preference, you can have the choice of using bars or lines when you're looking at your single channel measurements. So if I go back to spectrum, we can see that I'm operating within a line fashion. But I could just as easily change that to show bars here. And now we end up with something that looks more attuned to what some of you might have seen in the past with 1/3 octave RTAs. I'm not a big fan of the bars, so I tend not to use them. I prefer the lines. So, continuing on through our options, we want to go to the transfer function tab next, and this is where we want to select multi-time window. And because that's what's going to give us those multiple FFT sizes simultaneously, and it give us a more easy to read measurement. From there, make sure that your frequency scale is set to 1/3 octave. You have proportional plane or proportional panes enabled. And then in terms of phase, you want to leave both of these boxes unchecked. Under coherence, you want to show coherence and set it to 1/4 of a height. We'll talk about phase coherence here in a little bit. So that's pretty much it for the configurations.
What's the 1/4 height?
I'll show you.
Because I didn't have that one checked.
It's not critical to the operation of it. I just believe that it makes it exponentially easier to interpret. So we'll go here to our transfer function. Just a little side note here. I prefer to see my FFT setup as magnitude over phase. Smaart by default has it set up to phase over magnitude. So we'll show you here. We'll do a little FFT. So we see here with this phase how it's all hacked up and really jumbled there. What that's showing us is that that there's still a time offset here. We need to use Smaart to calculate for the internal latency of the computer, the I/O device, and the console. Just the whole round trip latency to go from the computer back to itself. So by doing that, we'll play pink noise. And then you want to come down here to find delay. You'll then see here within the delta delay parameters, that's showing you what the total round trip latency is of the process. So we go to insert, and we can see our actual phase trace here. Another option for doing this is you can click within that FFT window and just hit the key L, and it does the same thing. So up here in red is what's known as your phase coherence. I have it set to 1/4 height currently. If we go under transfer function and we remove 1/4 height coherence and hit apply, we can just see that it gets larger. And when you're looking at something this close in the near field, when your phase coherence is pretty even, it's not a big deal. But let's see what happens when I actually move the microphone back and we start to pick up more reflections. Pardon me. So you can bear with me taking up a little bit of your space for a moment. So we're pretty far away from the speaker now. We're going to see a lot more reflections now showing up in our measurement. And that's going to manifest itself within the phase coherence. So we need to recompensate for our time offset. So all of these little dips here, that's showing us that we have less valid coherence data. The phase coherence works very similar to a gate in the sense that wherever you set the threshold over here is determining what level of validity of data you want the FFT to take into consideration. So if I put it all the way down here, we're going to say that we're going to take in every bit of data that is greater accuracy than 20%. And then as we move it up here, now we're saying that we're only going to take in data that's valid beyond 80%. When you're doing these kind of system calibrations, you have to play with that threshold, and it's a constant give and take of how accurate you want your data to be. Ideally, you want to set your threshold as high as possible, but in the real world, that's not always an option. And so this is where your question comes into play about 1/4 height of coherence. This is normal height of phase coherence, and so we can see that these troughs, or these little stabs here, come down pretty far. By going back to our transfer function window and we change coherence to 1/4 height, we can see that it just takes up less real estate on the screen. And that spacing between 80% and 20% becomes more narrow. And so for me, having it set to full height, it's just visually, it's too much going on in the screen. So let's do some more pink noise to reset our time. Now you guys see how much nicer the phase coherence looks now that we're back closer to the speaker, because we're getting far more direct sound than we were previously. So because that coherence looks so nice, we can trust that our data is going to be valid. So now you'll have to bear with me. I've got to switch this back to my preferred viewing method of magnitude over phase. It's a Meyer thing. Now, something you all might have noticed here. So I mentioned that this portion right here of the phase trace is showing that all of our data is arriving at the same time. Does anybody have any opinions as to why we're seeing that the The most consistent arrival time is showing up at 100 or minus 162 degrees of a phase offset. And this kind of goes into the rabbit hole discussion that Frank and I were about to go down with these reference mics, is the DBX reference mics that I use and the university owns. They're all wired out of polarity from every other measurement mic in the industry. So because of that, when you use these, your nominal phase, or your phase that is arriving in time, is not going to show up at the 0 degree mark. It's going to show up far closer to the 180 degree mark because of that polarity reversal. Does that make sense? Mm-hmm. And you guys all know that phase and polarity are not the same thing. So our next move, because if we're doing this in the real world in like a PA tuning application, we want to be able to get several points of data. We don't want to just calibrate our sound system based off of one location, right? So we readjust some level. And we're going to store this trace. Now, just as I mentioned that about the fine delay function, there is also what's known as the delay track function that you can see right here. By engaging this little yellow dot, Smaart is going to auto-calculate the delay as we move this microphone around. So you can see loss in high frequencies within our second trace as we started to move off axis slightly. But what do you guys think about this right here? We see we have this dip in coherence, and we know that our phase coherence is telling us how accurate that particular data point is. So what do we think that this might be an indication of? Well, we can see that it's occurring at, we'll say 8K, and then we have another dip here at 13K, and then it continues down to about 18K. So what, to me, this looks like is a result of comb filtering, probably brought on by an actual reflection off of one of these tables. It could even be a reflection off of this portion of the speaker. And if we wanted to, we could actually mathematically determine where that reflection came from based off of the period of that wavelength. So we don't need to go that far into it. All that is just to say that as you move your microphone around, you're going to see different anomalies in the room, different reflections, different characteristics. Calculate our time offset. And so now we will store this. And here we will come over to our console, or the system processor that we're using. Excuse me, and we are going to mute the mains and unmute our sub. And so do you guys see up here how low the phase coherence is after probably about 600 hertz or so? That's because there's such limited data within within the content of this speaker. This is telling us that we can't trust anything that we see above 600 or 700 hertz. Make sense? So now we see the crossover that we have here, and we can tell that it's occurring roughly between probably about 120 or so down to about 275. When you think about crossover points, even though in our technology and our devices that we use, we set a very specific crossover frequency, 80 hertz, 90 hertz, whatever it may be, but you really need to think of it in terms of an entire crossover region, because we want more than just one frequency of phase and time alignment in our system. We want to go for a more broadband alignment to where we're arriving in time at this whole region through here to maintain proper summation. Does that make sense? Cool. So now that we've done this, if we come down here to our phase window, we can see that we've got a pretty similar curve going on here between our two sources, but they're not lining up. Ideally, we want those traces to be right on top of each other, maintaining the same shape and arriving at the same degrees of time. So, if you guys remember what I said earlier, a key difference in how we view phase and polarity in Smaart is by looking at the shape of the curve and where it falls in line. If the shape is maintained relatively constant between the two sources, then we can tell that the phase is relatively consistent. They should be arriving at close to the same time. But we can see that that's not the case here. So, since we know this phase trace is consistent, the next viable option to check is to determine if these sources are actually in polarity with one another. So if I reverse the polarity on the subwoofer, let's see what actually happens here to our phase response. So you can see it just moved up. It went from, it was previously where the blue trace is, now it's here. It just shifted 180 degrees forward. But we can also tell that even though that's the case, it's still not quite lining up the way we want it to. You know, there's a bit of degree of separation here, and it starts to vary more as we move down. So because we know now that the phase traces are not identical to one another, then there is a bit of a time offset that we're dealing with here. So if I come back over, we're going to start adding delay to our subwoofer, and I'm going to do this incrementally so you guys can see how this changes. Okay, so this is 0.1 milliseconds of delay. There's 0.2, 0.3, 0.4, 0.5, and 0.6. So now we have a trace that lines up a lot more. You see, we're actually maintaining a good overlap down both sides of the phase trace. And because we know phase is not just a relationship of time, it's also a relationship of level and how those two things interact with each other. So you want to maintain equal phase at any point in time when you have a level that is less than or equal to 10 dB. So if there's a 10 dB or more offset between two signals, then their time relationship becomes negligible. Anything less than 10 dB, then you're going to start to see some degree of summation or cancellation. So now if we play both the subs and the tops at the same time, we should see 6 dB of summation here in the crossover region. So previously we were looking at around 0 dB, and we can see up here that we've maintained a full 6 dB increase within our crossover region. Does that make sense? We all know that when two identical signals sum together properly, it creates an additive 6 dB of gain. So the next point to talk about here is this FFT that we're looking at. That all looks pretty flat to me, with the exception of a few peaks and dips here and there. Do you guys have any opinions about what it means for a speaker to be flat? Like, what does it sound like for something to be flat? If not, that's a good thing, because this is something there's a lot of misconception about. So to have a flat FFT, that's not a tonal flatness that we're hearing. All a flat FFT means is that what the signal is that's going in is the same signal that's coming out. It's not being altered by the individual components of our sound system. That's what it means to be a linear speaker. But if I go through and I play some program material, we can observe with an RTA how that changes. So I'm going to play Pink Noise again. So we can see that looking at Pink Noise, there's a bit of consistency there with our FFT, but if I come over here and I start to play some music for you, you should be able to tell the tonal variation between some of these songs. So notice the FFT up here has not changed from what it actually was with Pink Noise, but we can see that our RTA has changed quite significantly.
With a great big heart, and everything you know just falls apart.
Again, no change to our FFT.
I can see God in Italian shoes, with a beard and a gun and a cage.
Don't be cautious, don't be kind. You committed, I'm your crime. Push my button.
So we've just gone through several different songs, and spectrally they all sound quite different, and we can see that manifest itself down here with the various RTA responses that we have. But other than just the changing in overall level, our FFTs remained constant. Does that all make sense? So when we talk about having a flat sounding PA, what we're really saying is that we have a transparent sounding PA. We don't really want something to sound flat necessarily. We just want it to sound consistent.